This is going to be a walkthrough on the Parametric Equations, Polar Coordinates, and Vector Functions project. You can access the presentation that I'm going over today in the AP Calc VC help files under the folder for the module. So part one says boosting your cell phone connection. So depending on your location, a cell phone does not receive the same transmitting signal from the service provider's antenna. This is because the radiation from the transmitting antenna is not uniform in all directions. The intensity from one company's antenna is given by the polar equation R equals 2 cosine squared theta, and a competing company's intensity equation is R equals 4 cosine squared theta. So first I would recommend graphing this, which is what part A asks you to do, model the radiation intensities of both companies on the same graph. So if you're using Desmos, and you may already know this by now, you need to change the graph to polar, which you can do by selecting the wrench here in the upper right hand corner, and then select here, this is polar. This is the rectangular or the Cartesian system, and this one's the polar. So you can change it. And then once you change it, you can input the polar functions, use just as they appear here on the page, R equals 2 cosine squared theta. And if you just type the word theta, it will automatically update to the symbol theta. And that's the easiest way that I found to use the polar grid. Just for your convenience, I do already have over here to the left a table of values for these functions. And I did already set this up so that the critical values or certain values here are shown. Like for instance, 0, pi over 2, pi, 2 pi, 3 pi over 2, critical values here. So I don't know exactly how, R and theta are, let's just say I don't know how R is defined. Theta is going to be some sort of a degree measure, a radian measure. But I think that we can assume that the greater the intensity of the antennae, the better quality and farthest reaching signal can be used. So even though we might not know visually how that theta is measured, I mean, is it measured from the horizon? Is it measured from, wherever? I don't really know that, and you could probably do some research on the internet about that. But what we really do know, and the only thing that we need to know, is the more intensity, the better quality of the cell phone signal. So let's take a look at this table in detail. And we can see from the table over here that when theta equals 0, this somehow this variable theta translates to the location of the phone. So when the phone is at theta equals 0, we can see that the intensity of the antenna is at R equals 2. And then going down through the other possible values of R, we can see that it never reaches a value more than 2. As opposed to the other function for the competing company, we can see that it has a stronger intensity at R equals 4. Okay, and we can probably conclude, even before we graph it, that they're going to have the same general shape. They do have a different constant there in front, the 4 and the 2, but they're both cosine squared of t. So let's keep reading this. So again, like I said, we can see from the table that the intensity will never be greater than 2, and the intensity is at 2, or at its greatest, at these values, pi equals 0, pi, and 2 pi. So you can see that from the table, that is, I guess, what you would call our maximums. And 2 pi is actually equal to 0 on the polar graph. Remember, The polar graph goes from 0 to 2 pi, but 0 is equal to 2 pi, so we can disregard that value because that's just when it circles back around. And we can confirm this on the graph. So if you want to, you can graph that if you want to pause the recording and do so. And I think that we can really conclude from this that to get the best quality signal, the cell phone would be used at these locations of pi, theta equals 0 and theta equals pi. So none of this I'm going over right now answers the question for part A, because part A is just the graph, but we're just trying to get a general understanding of what these polar functions represent as it relates to this application of the cell phone. So we can also see that when theta equals pi over 2 and 3 pi over 2, the intensity is 0, and at those locations, cell phone service likely doesn't exist. So let's go back over here to the table for the first cell phone company. You can see that R equals 0 right here. So more than likely, we do know that there's no intensity there because R equals 0. So I would assume that means that there is no cell phone service at that theta, which is pi over 2. Then here we can also see, and I didn't type those in. It's a little odd how those are showing up. It says 3 divided by 2 pi, which really is 3 pi over 2. But that's just, I think I did this in, I didn't do this one in Desmos. Either way, that's how it prints it. And all other values in between 0 and 2, or 2 and 0, depending on where you're starting out, are just somewhere in the middle. Not the best signal, but not the worst signal. So now that we have a good understanding of how these functions work, you can graph it if you'd like. I'm not going to graph it for you, but if you want to take a look at the graph before we move on, it would probably be a good idea. So part B says find the area of the geographical region between the two curves and describe what this means to potential customers of each company. And then explain exactly where you would be located so that it wouldn't matter which company you use. So now that you understand the application of these graphs, you should be able to answer these questions. All right, moving on to part 2, which is what a lot of you have asked me to go over. I can definitely help you with that today. Part 2 is called rolling along. Ever wondered how fast a hula hoop is moving when you give it a push and it rolls along the floor? Consider a special hula hoop that has one very narrow black band painted around it. So I think the hardest part about maybe this problem is using this figure provided and visualizing this. So let's suppose that you are, you're standing on, a flat piece of ground or concrete. You're holding a hula hoop in your hand so that one end of the circle is in your hand, the other end of the circle is touching the ground, and you're going to use your hand to push that hula hoop, and it's going to roll, as in, I would say, perpendicular to the ground. So right here where you see this black band, that is the part where it is initially positioned right on the floor or the concrete or the ground, and then you're going to push it. So let's say that your friend now is holding the hula hoop and you're standing out to the side watching it. Think about the position of that band. I'll see if I can sort of draw a picture for you. So let's say, let me see here. Hold on just a minute. All right, so say here's the hula hoop, and you or your friend standing right here. You've got the black band right here, and you're going to push the hula hoop in this direction. So that black band is going to do something like this. Then it's going to touch, And if it keeps going, it's just going to, that black band is going to continually take that path. So that is the position. So that's what we need to, I guess that's the key word here, is where that black band is positioned. So the path traced out is given by this position vector. So in order to graph that position vector, if you want to use Desmos, you just type it in as you see there. You'll notice that when you graph it, well, I guess I should go back. One period of this function is 2 pi. And what that means is that this is one time that the hula hoop makes one full rotation. That's another. That's another. And it takes one period of 2 pi to make that full revolution or rotation of the hula hoop. So that's why I selected 2 pi. You could really use anything that you want to. Just, understand that 2 pi is the period. So in order to really see the full graph, you're going to have to at least use 2 pi, 4 pi, 6 pi, 8 pi, to really make that graph look neat and to be able to notice the patterns. Also, right here where you define the domain of t, that automatically pops up. And I think it automatically sets it at 2, so you'll have to change it to 2 pi. Okay, so graph the vector function, that's part A. So I already told you how to do that. It says to make certain to include your window settings and provide justifications for your settings. So we just went over why you use 2 pi and all of that. If you're using Desmos, you're already going to have the scale and window will be on there. If you're using a handheld TI calculator, then you are going to have to also take a screenshot of your window settings since that doesn't appear on the same screen as the graph. So part B says, what are the vector functions that represent the velocity and acceleration? So backing up a little bit to applications of differentiation module. So you learned in that module that if f of x is the position function, then f prime of x is the velocity function, and f prime prime, or the second derivative of x, is the acceleration function. Well, this is much the same, except that you have to take the derivative and second derivative of a vector valued, oh, little typo there, vector valued function. So you can learn how to do that in the module, but that's really all there is to it for part B. So if you don't remember how to take the derivatives of vector valued functions, or even the second derivative of vector valued functions, then go back and review that, and that will help you with part B. Part C says find the maximum and minimum values of the velocity vector analytically. So yes, you could graph the velocity function you found in part B, but it says to solve this analytically. So plus you're going to do the graphing part in part D. So again, remember, just like you learned in a previous module, which was, I think, the applications of differentiation module, you can use the first derivative test to find the minimum and maximum of a function. And essentially that's what we're doing. Now it is a special type of function because it's a vector valued function, but it's the same process. Once you have that derivative, then you set it equal to 0. But to do this, we first need to find an equation that represents the magnitude of the vector valued function, because that's what we're going to actually set as equal to 0. Because let me see if I can go to the next page. Yeah. All right. Well, I really need to draw a picture for you. Hold on just a minute. I'm going to add a new pod so we can kind of review what I'm talking about and then apply it to this example. All right, so you remember that in the first derivative test, if you take the derivative and set it equal to 0, it will give you the points for the maximum and minimums of the graph. Remember that it will also give you anywhere the derivative is 0. So it could even be just where a graph continually or a function continually increases, but does hit where the line of tangency does have a slope of 0. But either way, that's what the first derivative test does. And what that value finds is the maximum and minimum, which is going to be, you might be solving for x, but then when you plug the point in, your maximum value is going to be like y equals, and if this is 2, it might be like 2, 4, and -1. So these are your maximum and minimum values. You might even say, with the actual coordinates x and y. So with vector valued functions, you're going to be essentially doing the same thing, except you're going to be finding, I guess, like the length of this vector, and the length of that vector, which you want it to be either the maximum length or the minimum length, because that's what the question was asking us to do. So in order to find the max and the minimum, which it looks like it was cut off here, so let me copy and paste that into well, it's not on there. I'm not going to copy and paste, but you can go and refer to this presentation, but I'll fill it in right now. Hold on. Get my draw. All right, so to find the max and the minimum, find the first derivative of the magnitude of v. Now this is going to be in terms of t. So keep that in mind. Let's see here. How else maybe can I help you with this? Let's see what I've got on the next page. That's the last page. So hopefully that makes sense, but the velocity function represents the speed at theta, which does vary throughout the function more than likely. So if we're looking for the maximum minimum speed, we are looking for the magnitude or length of that vector. Okay, so I think that maybe wraps it up in a more clear words there. This picture here, I want to clarify, has nothing to do with our problem. It's just really a picture that I wanted to show you that would show you like that this vector has a theta, and then it has the velocity, which is represented by the length of the vector. Okay, so find the maximum and minimum values of the acceleration vector analytically. So that's going to be pretty much the same concept as part C. So in order to find the maximum and minimum, find the first derivative of the magnitude of A. So I really think that probably C and D are going to be the most challenging parts of this. There is going to be a good bit of calculus that you need to go through for this, and your answer is not just going to be like the maximum is 4 or whatever. There's really going to be some in-depth analysis on those. So if you need any help with that, just email me and we can discuss it by email if you want to run by me, run by what you're thinking all of this means. Part E, so here's where you're going to provide the graphical representation of the velocity and acceleration vectors. Do they confirm your answers to C and D, and explain? So since you already know how to graph vector valued functions, you can do this, and then all you'll have to do is just interpret the results. So you'll have a graph that has the position function, the velocity function, and the acceleration function, which is basically the function, its first derivative, and its second derivative. So consider, as you look at that, consider the domain and range of the graph and visualize those hula hoop revolutions like we talked about, and how the velocity and acceleration are related to those revolutions. So, the increases, the decreases, that kind of thing. Okay, so now we're going to, I think this is going to be much easier than the previous parts. But suppose a friend wants to join in the fun and has a smaller hula hoop with a similar narrow black band painted around it. The black band hits the floor twice as many times as yours. So part F is, what is the vector function that models this behavior? So once again, you're going to be writing the vector valued function. Then on part G, you're going to compare the past. So you want to take your answer from F and graph it with your original hula hoop position vector. And then just determine what their similarities and differences are. So really, it can all be summed up in the scenario that I have there underlined. The black band hits the floor twice as many times as yours. So think about what the graph of the position vector valued function will look like and rewrite that function. You can use just your properties of transformations for trig functions. That should help out. And, type in different numbers, see what you can make work so that the black band does hit the floor twice as many times as yours. Also, compare the size of the hula hoops. I mean, not that you know the exact size, but you should be able to write proportions of those. The period of the graphs, like, how much in terms of maybe the time it takes for the band to hit the floor twice as many times. And also provide a copy of your graphs with the settings. So hopefully, I think that was the last slide here. Yes, it is. So if you have any questions, let me know and I'll be glad to help you. I think this will at least get you a very good start to the project. Have a great day.